In 1951, Alan Turing delivered a stark warning. He pointed out that once a machine thinking method had started, it would not take long to outstrip our feeble human powers. Today, the tech industry is chasing the ultimate endpoint of Turing's prediction: artificial superintelligence. To build a flawless supermind, engineers need it to possess three specific traits simultaneously: perfect accuracy, universal trust, and human-level reasoning. But as researchers dig deeper into the foundations of artificial cognition, they've uncovered a hard truth. You can pick two of these traits, but you can never have all three. The mathematical reality is that accuracy, trust, and human-level reasoning are mutually exclusive. To see why a perfect AI is a mathematical paradox, we have to look at how we teach machines to think. We need to climb the ladder of logic, rung by rung, to see exactly where the math breaks down. Curious, analytical. At the very bottom rung of artificial reasoning is propositional logic. In this system, AI operates under the closed world assumption. This is a strict rule stating that if a piece of information is not explicitly written in the machine's database, it is automatically assumed to be false. Look at this excerpt from a journal on knowledge engineering. It highlights the exact trade-off of this approach. Propositional logic gives a machine total certainty, but it has no support for variables, quantifiers, or the internal structure of statements. This rigid assumption makes an AI unbeatable in a closed system with perfect rules, like a game of chess. But if you put that same machine into the real world, where data is messy, undocumented, and unpredictable, the entire system crashes. It simply doesn't know how to handle the unknown. To fix that, engineers had to move up a rung and try to give machines a version of human intuition. They introduced non-monotonicity and default rules. As this lecture slide shows, if an AI is missing information, it can now use a generic prototype to fill in the blanks. If it hears bird, it assumes a robin, not a penguin. It can guess, but letting a machine guess introduces new logical bugs. The most famous is the Yale shooting problem, which demonstrates the frame problem. Imagine an AI loads a gun, waits a few minutes, and then tries to fire. Because the environment changed over time, the AI struggles to carry over the assumption that the gun is still loaded. It loses track of the state of the world. Then you have the horizon effect. If an AI encounters an unavoidable negative outcome, it often can't solve the problem. Instead, it uses delaying tactics to push the failure slightly out of its immediate search depth. It hides the problem just over the horizon. We learned that manually coding rules and exceptions to simulate common sense just creates a fragile house of cards. The real world has too many variables to hard code into a single, flawless system. So engineers stopped trying to script the rules. They moved to the modern era of deep learning and neural networks, building systems that absorb data and learn directly from their environments through trial and error. This approach is highly effective, but it's prone to a phenomenon called catastrophic forgetting. Say you train an autonomous car to stay in the center of the road. It learns that the center is safe, but by hyper-focusing on that safety, it can completely overwrite the memory that the edge of the road is dangerous, causing it to suddenly and inexplicably swerve into a ditch. There is also the issue of transient sensor failures. If a robot's camera breaks and starts feeding it persistent static, the AI doesn't realize the sensor is broken. It confidently updates its worldview to conclude that the actual universe has suddenly turned into static. Modern learning models navigate complex real-world environments by operating as an opaque black box. To gain this adaptability, we sacrifice strict logical accuracy. This brings us to a hard mathematical boundary. A recent paper by researchers Panigrahi and Sharon proves that this limitation is a foundational law, echoing the historical limits of computation established by Gödel and Alan Turing. Their formal proof goes like this. If an AI system is strictly accurate, meaning it is hard-coded to never make a false claim, and it is fully trusted by users to maintain that standard, it mathematically cannot match human-level reasoning. This diagram maps out the time-bounded halting problem. A human can look at a specific logical puzzle and easily deduce the outcome within a set time limit. But an AI bound by strict accuracy cannot take the leap of intuition required to guess. To absolutely avoid a false claim, the machine is mathematically forced to hit a wall and output, "I don't know." This forces a permanent ultimatum on developers and society. We can build AI that is highly adaptable and intuitive, but we have to accept that it will eventually hallucinate and fail. Or we can build a system that is perfectly safe and accurate, but it remains rigid, easily confused, and unable to match human intuition. A flawless, perfectly trusted supermachine remains a mathematical impossibility. More processing power or optimized code cannot circumvent the basic logical rules dictating it cannot exist.